In this video, we're going to solve a classic geometric problem, finding the area of a shaded region. It's a beautiful combo of circles, polygons, and a little bit of logic. Let's jump in. Here's what we're looking at. A regular pentagon is perfectly inscribed inside a circle. That means all 5 of its corners touch the edge of the circle. We want to find the area of the shaded region, the space between the pentagon and the circle. To make this manageable, we'll break the shape into 2 parts. First, the entire circle. Second, the pentagon inside it. If we find the area of each, we can subtract the pentagon from the circle to get the shaded region. So the plan is simple. Find the area of the circle, find the area of the pentagon, then do a quick subtraction. Circle minus pentagon equals shaded region. Let's start with the circle. The area formula is straightforward. Pi times radius squared. But we don't know the radius yet, so for now, we'll keep that formula in our pocket and move on. Now, let's focus on the pentagon. It's a regular pentagon, and all the sides are the same length. Let's call that length A. And that'll help us build a general formula. Here's a great trick. If we draw lines from the center of the pentagon to each of its 5 vertices, we split it into 5 identical triangles. Each one is isosceles because 2 sides are radii of the circle, and the 3rd side is the pentagon's edge, A. Now, take a step back. Those lines we drew from the center, they're radii of the circle. So the 2 equal sides in each triangle are R, the radius we're trying to find. Let's figure out the angle at the center of each triangle. A full circle is 360 degrees. We've split it into 5 equal triangles, so each central angle is 360 divided by 5, which is 72 degrees. To make things easier, let's cut one of those isosceles triangles in half. That gives us a right-angled triangle, where one side is half of A, one side is R, the radius, and the angle at the center is now 36 degrees. Now let's use sine, because we know the opposite side, half of A, and we're trying to find the hypotenuse, R. So we say sine of 36 degrees equals A divided by 2 over R. Solving that for R gives us R equals A divided by 2 times sine of 36 degrees. Now we have a formula to find the radius in terms of A. Let's keep that handy. We'll need it very soon. Let's now find the area of one of those triangles. We'll use the trig area formula. 1/2 times 2 sides times the sine of the angle between them. In our case, both sides are R, and the angle is 72 degrees. So the formula becomes 1/2 times R squared times sine of 72 degrees. Since there are 5 triangles in the pentagon, we just multiply by 5. Area of the pentagon equals 5 times the area of one triangle. Now, let's go back to the circle. We've already got a formula, pi times r squared, and we now know how to calculate r, so we're ready. Let's remind ourselves what we're doing. The shaded area is area of the circle minus the area of the pentagon. So now we'll plug in our formulas. Circle is pi times r squared. Pentagon is 5 times 1/2 r squared times sine 72 degrees. We simplify. Both shapes involve r squared, so we can factor that out. Then, once we've got the expression, we substitute in the value of r we found earlier. And that's it. We've split the complex shape into 2 simpler ones, found the radius using a little trigonometry, calculated the areas of both the circle and the pentagon, then subtracted to get the shaded region. A mix of geometry, trig, and smart structure, all leading us to one clean result.